So let's go through the design process. If you look at the design process, traditionally it is supposed to be like this, that you start with the conception, and conception basically means that you conceive the structural system. That is the first part, that what is your structural system, and what second part of that is design criteria, which also we will discuss. So the first part is to just set up what you're going to do, the concept level. Then once you finish the concept and you're satisfied with the system, and you do some studies on that, which we talked about earlier, then you go to modeling, and that's where ETABS will come in. So you start to create the structural model of the concept that you have created, and then that will typically be in a software. And in our case, we will use the ETABS software. And then once you have the model, you modify it, and then you do the analysis, also maybe the same program, and then you get the forces, you check the load shape, we will talk about all these things step by step. Then we do the analysis, then we do the design. Design can be done automatic by the program or manually through Excel. So some people export the results from analysis to their own Excel sheets or their own procedure and do the design. Some people do the design inside the program. So for small projects, automatic design might work. For big projects, most companies have their own design procedures which they link to API. So one of the things that you should learn is also the use of API, how to connect the ETABS with your own short script or program, so you can extract the data and do something manually. So advanced users, or if you really want to be called an advanced software user, you should learn API. So you can write short programs to process the data by yourself, because programs sometimes have limited ability to give you the output. Then you do the detailing, generate the details, and then drafting and costing. So that's the process that we will follow. And sometimes all of this is integrated, like this one. This is text, and this is integrated. So you can go up and down. Now ETAB, for example, is quite integrated. It goes all the way to getting the estimates. So you can go through this process in the whole program. And this is, as I more explained further, so you will get the architectural plans or functional plans. Then you will do, I see, so you want me to be here, okay. And then go to structural system, and from there to trial member and section. And this is the most tricky part, this section on how to start the model is, you will be stuck at this point, because the analysis program like ETABS, they ask you for the dimensions before you can do the analysis and design, which is the funny part, because in the design we are trying to find the column size and beam size, but for the analysis you still need it to start, which means you have to estimate these sections, these sizes quite well. Because if you make a wrong estimation, you will get wrong analysis, you can get wrong design. So it doesn't work. So that's why, for example, if you do this one, trial member and section, you do the modeling, you do the analysis, you get to member design, you check, it's not okay. Beam is too small, column is too small. You have to come back, revise, and then do the modeling again, and then keep on doing it until you find the right answer. And this can take a lot of time if you don't have experience. That's why the experience comes in, how to start with the good sizes, and we will talk a little bit about that. There are some thumb rules, there's some preliminary calculation. Of course, AI is the best for this part. So AI will be very useful at this stage, okay? And then we go to that. So this part is called conceptual design, and this part is called modeling analysis. This is called design detailing, and then we go on. In big projects, in big firms, these are three different teams. These are normally done by three different teams. This team is different. Senior people do that. Then an analysis specialist do the analysis, and the design specialists do the design, and drafting is done by still another group. So in a large company, you will see that there are all of this is done by different groups. Okay, so what is the intent of the design? Why are we doing the design? Why do we do structural design? That's a very big question. Why do people give the project to us to do the design? What is our main role? So our main role is public safety. So we have to ensure that whatever we design is safe for the public, because it's an obligation that we don't create something that will harm people or will not save people during any hazard. And to minimize damage to built environment, damage will be minimum. Not only safe, but minimal damage. And then preserve continuity of life. That means it should remain operational throughout its life. Now this is intent, this is the intention of the design. But satisfying this intent is very, very hard because design codes and guidelines, they don't know your structure. They just have guidelines general. But each structure is unique, each location is unique, each soil is unique, each configuration is unique. So how can we satisfy that each one will be actually safe? And that is a big responsibility and also a big challenge, how to do that. And we will talk a little bit about that today. So basically for the buildings, tall buildings, we have three challenges to tackle: the gravity loads, people, things, wind loads, and earthquake loads. So they are all differently applied, very differently. Gravity load mostly generated by the mass of the structure by itself, plus people, things that we place on it. Wind is an external load created, some direct by pressure, some indirect through the wind profile around the building. Okay. And I think you will learn about this from Professor Penning's class. An earthquake, of course, is not a force, it's not a load, it's a movement. So the ground is moving, and because of that movement, then the structure itself generates a load. So it's not a load coming from outside. It is a load generated by the structure because it is trying to resist the movement. So that's a very different type of loading compared to the other two, because it's basically generated by the structure. Because it is generated by the structure, we can control it. Same is the case with wind. Because it is generated by the form of the building and its movement, we can also control it. So because we can control these two loads, makes it even more hard, because the loads are not constant anymore. Loads will not depend on the structure that you are trying to model. So unlike live load or dead load, which is kind of constant, these loads are generated by the structure form and stiffness and its own behavior. They interact with the loads. So the load is not only the section is not known, the load is also not known because it can be changed after you finish the design. And that is the key difference between tall buildings and smaller buildings. So this slide I tried to show you last time. Basically, the movement is very large here. Okay? And the next one is actually a collapse. Yeah, and that's a collapse. So these are failures which will happen even if you design the structure for the light load. I'm sure those people who design pavilions, that failure or collapse many times happens so many times. They design for the code specified light loads. They take into the decking. But the vibration was matching with the natural frequency of the structure. So you have what is called the resonance effect. And that resonance effect increases the displacement and load many times. And that if you don't analyze it that special, then you cannot handle it, because the codes loads are not for a specific structure. So even if you follow the code, the safety was not guaranteed. So the intent of the design was to make it safe, but it was not. And this happens quite often. Last 2 years has not been good for bridges. So many bridges have collapsed around the world. And many of them because they have special conditions in that location, which is beyond the traditional codes that we use. So this is just to give you an overview. We will discuss more in detail about the design criteria later. So dead loads typically come from the density or the self-weight of the structure. And normally we have to minimize it. So we have to use the material with the least weight. We talked about this with the highest, longest specific length and so on. Second one is the sequence of loading of dead load is very critical for tall buildings and also for bridges. Short building doesn't matter. But when you make a building like that one, they will construct one floor first, then they will make another floor on top of that, then another floor, until they finish the whole building. But most people who are not familiar, they just create the whole ETAPS model one time and then apply the load one time, all the dead load on all of the building at one time, and as if the building is there without weight, and suddenly you switch on the weight at one point. And this is not the same as constructing the building floor by floor and loading floor by floor. The two are very different. They will create very different distribution of forces, internal forces and displacement. And if we don't manage this one, you cannot predict the real response of the building. So for a tall building, it is essential that the sequence of construction and sequence of loading is incorporated into the design process. So when you run your model in ETABS, you should run construction sequence also, not just run the model and apply the load and get results. And this is again, once again, we will go to more detail of this one. But I just want to make sure that the dead load, the gravity load, must be analyzed step by step as it is constructed. So the construction methodology, construction technique, construction process needs to be known or specified for the tall building to be properly analyzed. Live load is a major kind of an issue in tall buildings. First of all, we talked about multi-use buildings. So each building has different multiple use. Hotel, library, apartments, office, all in the same building. So every floor has different live load specification. And the challenge comes because the building owners can change the use later. Let's say they could not sell the hotel rooms, they change it to office or something, or office did not sell, they want to make it into a hotel now. All the loading criteria will change. Right? So which means that we have to anticipate change of the occupancy of a building and make sure that that will not create a problem right, within that. The second issue is that the live load is not applied at the same time in the entire building. For example, the specified live load here is 2.5 kilonewton per square meter or 2.2. Then, if you have one floor, is fine. Even now, we don't have enough. But if we have 30 floors, it is unlikely that all the rooms will be full to the full live load at the same time. So when you calculate the load on the column, if you just add the live load on every floor, you will be making a big mistake because you will be overestimating the live load, which cannot be realistically present. So there is a live load reduction factor, which is included in the calculation in the codes. And once again, when we do the design criteria class, we will look into that. So every building code has their own way to calculate live load reduction factor. So for tall buildings, live load reduction factor needs to be included. So depending on number of floors, number of area, number of things, they ask you to reduce the live load for certain part, for certain design. For floor design, you cannot reduce. For foundation, you can reduce. For column, you can reduce. Things like that. So there are rules about that. So we need to be aware of the live load reduction and we need to be aware of the sequential dead load application. Then the biggest challenge comes to now this one, the wind and the earthquake. These two are very, very different animals, if I can say, although most people think that they have both of them apply horizontal force on the building, but that is not true. Their design concept is opposite, their whole application is opposite. First of all, as I mentioned to you, one is an actual force generated on the building by wind particles hitting the building and wind particles flowing around the building. So in tall buildings especially, two types of forces are generated. One is along the wind, which is the pressure on the building, and one is across the wind, which is the wind is flowing around the building, it creates vacuum, and the building will move to the vacuum or low pressure zone from the high pressure zone. So that is even worse than the direct one for many buildings. So we have to consider both the direct pressure from the wind, which is the hitting of the wind from the wind direction, in which the building will deform in the direction of the wind, but at the same time, building will deform perpendicular to the wind. Because when the wind is flowing around the building, it will create vacuum, low pressure zones, and if the building is not symmetrical, they will not be equal. And also, there's something called water vortex shedding. because wind is not constant. Wind is blowing slow, fast, slow, fast. When it does that, the pressure changes on both sides unequally. So the building starts to move in that direction. Even though wind is this direction, building starts to move in the opposite direction. That is very dangerous. So we have to prevent this crosswind movement or a crosswind, oscillation of the building. So both, and that effect normally the building codes do not handle well, because building codes are not developed for tall buildings. If you read the building code, they will tell you that this code is useful for buildings up to 50 meters or something. Right? Most buildings are not dealing with tall buildings. We need special codes for that and special handling of that. So for the wind is so unpredictable, so that almost every tall building must be tested in the wind tunnel. So you cannot rely on the wind calculated, specified by the building code or by the formula or by the analysis. You must put the building model in a wind tunnel and then test it for the wind around, because it will be affected by other buildings and so many things. So you must go and see the wind tunnel and see how it works. So this is one thing. So this is velocity. The wind pressure is related to the velocity of the wind and the terrain and many things, and it varies by the square of the velocity. So when the wind velocity is increased, the pressure increases by the square. And as you go high, the wind velocity increases. So the pressure at the top is much higher than pressure at the base. Much higher, several times higher. So that wind velocity profile has to be specified, and that can be calculated, and that is velocity, and it also produces acceleration. So not only velocity, but we also need to worry about the building acceleration, because acceleration can make people dizzy. So one of the key control on the building is acceleration due to wind that we have to check. And once again, codes will not give you any formula to calculate the acceleration due to wind, except Canadian code, some portion or some other. Normally they don't have it because they're not dealing with tall buildings. Now coming to the earthquake, seismic load, like I said, is a ground motion. Ground is moving at a high acceleration, and the building has a mass with inertia. Building doesn't want to move. The ground is moving, so building tries to resist the movement because of the Newton's law of the So because of the mass and the acceleration, force is the same. And that force is the one that we are worried about. And the higher the acceleration, the higher the force, or higher the thickness of the person, higher the force, higher the mass one. So we will talk about the dynamic very soon, and the whole dynamic. But the problem is that this force generated by the structure is highly dependent on how the structure responds. So we can manage to reduce the force by the earthquake by modifying the structure system, putting electricity, putting vertical displacement, putting devices, putting many things there. So for wind, the same thing. If the wind oscillation is high, we can put devices like dampers in there to reduce that acceleration. So both these forces are controlled by putting some devices in the building. So these are, for all buildings, almost every building will have some kind of mechanism to reduce these forces. If you don't reduce them, they are not manageable. So that's why both of these designs for wind and earthquake requires an understanding of dynamics and understanding of interaction between force and displacement and acceleration and rigidity and all of that. So that's the basis. But the two are opposite. The problem that if you try to solve the wind, it will make the structure bad for earthquake. And if you try to solve the earthquake, it will make it bad for the wind, because the reason is this. The two are designed for completely opposite ends of the design. Wind is designed at this point, which is the elastic limit of the elastic portion of the response, linear elastic. So for wind, we expect the building to remain linear elastic. We don't want any nonlinearity. We don't want any damage. We don't want any rigidity. We want the wind force to not cross the linear range. So building has to be stiff and strong to resist the wind. But for earthquake, it's the opposite. We want the building not to be elastic, but to be inelastic and highly nonlinear, which means we want the structure to be ductile and soft. So if that is the case, then the same building we try to design for wind, it will require it to be elastic and stiff. It goes to earthquake, we want the same building to be ductile and soft and not have high stiffness because we want to reduce the force. So this creates a huge challenge to design the same building for wind and earthquake. And this reduction, this R factor, that is the reduction factor assumed for the elastic to linear elastic to nonlinear response, is the key estimating factor in the building codes that people use to estimate the nonlinear response from the linear response. I will talk more about that later. I'm just giving you overview today. What are the challenges? So the challenge is to design the building for earthquake with reduced force and design the building for wind with the real force, keeping that elastic, keeping that inelastic. This is based on ductility and displacement. This is based on force and resistance. Okay? So the two are now not only opposite in the way they're generated, but they're also opposite in the way they are resisted and how the structural system is developed. So now the problem is buildings which are in the range of 40-story or 200 meter, both the forces are of the same magnitude or same nature. For buildings much higher, wind will take over. Earthquake will become less important. For building much lower, wind will not be so important. Earthquake will take over because the building is not high enough and the velocity is not high enough to cause a problem. So for low-rise building, earthquake will govern straight away. For very tall building, wind will govern straight away. It's the middle portion that we are talking about that the two will interact. Now, this is another interesting point which I think most engineers do not understand. They think, or most engineers think, that if my country or my zone is not a seismic zone, I don't need to worry about earthquake design or wind will govern, because they are comparing the elastic to elastic. They're not comparing with the ductile, that force with that one. So a certain factor of R is included to reduce the seismic force by a factor. This R factor varies between 3 to 8. For most building, it will be around 4 to 5 by the code. Which means if the force, calculated force is 100, you design the building for only 20. But for wind, you design for full wind. So even if the seismic force, now the problem is for that seismic force, you need to, that is based on the assumption that it will be reduced by yielding. But you can't go below wind. So wind will not allow you to go to 20 design, which means that there will be no utility, which means earthquake force that you assume will not be available, that R is not available. So your earthquake force will be multiplied by a factor to go beyond wind. So that interaction between the two is very, very unpredictable. Depends on the zone, depends on the wind velocity, depends on the earthquake, everything. So you cannot predict, you cannot compare simply by comparing the forces between the two, because the two are designed for the different factors. Right? So it cannot be that, oh, I calculate the bending moment from wind and I calculate the bending moment from earthquake, and bending moment from wind is higher, so I design for wind. No, because bending moment for earthquake was reduced based on a certain R, which will not be less than wind. So the earthquake forces must be elevated. So anyway, so this is more detail that we will talk about. So this is countries, both countries like Philippines, very high wind velocity 300 kilometers an hour. Seismic zone very high. Manila, Philippines, they have the highest seismic zone ground acceleration, and also one of the highest wind velocities. So buildings over there are in real trouble. Countries like Bangkok, very low wind, very low earthquake. But once again, the problem is the similar. It's not that we solve the problem, because both of them are so low that they're still fighting with each other. So every time we do some research, we give the thesis. I normally give them two topics. One, students doing the same topic in Manila, and another student doing the same study in Bangkok. So you get to compare two very different loading conditions between wind and earthquake. And there are countries where wind is very high, earthquake is like Dubai. Wind is high, earthquake is low. And there are other countries where earthquake is very high, wind is very low. So there are all kind of combinations around the world which are present. So each building is uniquely affected by these combinations. London, high wind, no earthquake. So buildings possible over there, not possible in Manila, and vice versa. So this is quite important that we realize that the building structural system and the two wind and earthquake zones will greatly affect how they will perform in that environment. Okay. Another thing, the understanding of how the loads go to the design. So we have loads. From loads, we go to load cases. From load cases, we go to load combinations. From load combinations, we go to design envelopes. From design envelopes, we can go to design actions. And for design actions, we go to design sets. This understanding is extremely important if we are going to follow the path from actual load to actual reinforcement. So for example, let's say I have a beam column here, and I get some reinforcement in the column. To trace the path, where did this reinforcement come from, you have to see what was the dead load, live load, wind load, earthquake load. Then, what combinations were used, and I can combine live load and dead load, and I can combine a live load, dead load with wind load, and I can combine dead load and live load with earthquake load, but I cannot combine dead load, live load, and earthquake and wind together, because unlikely for them, that combination is normally except for Chinese. People don't consider that. So the problem is that from load cases, load combinations are developed. And wind also, wind can be coming from this direction, could be coming from this direction, could be coming from this direction, any direction. So all around wind directions will produce different belly moment in the same column. Earthquake, the same thing. Earthquake can come from any direction. So it could be producing different belly moment depending upon where it is coming from. So direction of earthquake, direction of wind will create those cases from the same. So same wind load may have 24 cases of wind directions. So you are not going to apply wind just one time. You are going to apply the wind 24 times or 36 times or 12 times, depending upon how many angles you consider. Because each angle will produce different forces. So you have to analyze the wind load, which is one load, 20 times or 12 times. Earthquake, similar. Live load, many patterns. So each load produces many cases and they are combined in different ways. So dead load, live load combined in different order, with wind load combined with different order. Remember, wind load combined with 20 different directions. So suddenly, lots of load combinations will be generated, because you have all the possible combinations to consider. And from there, you will get for this column, maybe for a tall building, without nonlinear, you will get maybe 200 or 150 or 200 different belly moments for the same column. So now the question is, how do I design the reinforcement? Which one should I pick? And the first reaction for many people is, oh, I will take the maximum moment. He's shaking your head. And no, it can't be done. You cannot pick the maximum moment. You cannot take the envelopes. You have to go to the design actions and design action sets. Because in the first class, which I'm sure you've all forgotten already, we talked about the interaction. Any moment here, constant interaction. Any moment, ideal force, moment in the other direction. So everything is interacting. Nothing is independent. So you cannot take maximum moment, maximum load, maximum shear design, because they have to be part of the same set, which can be physically possible. So that's why we go to what is called the action set, but this one. So it's one way flat, we can just consider one very moment, maximum moment is present, because there's no combination. It's just a graph. But for me, we have to consider moment X and here inflection, or here important inflection, and here constant and moment interaction. You studied that last time. You look at the curves or the interaction between these. So they cannot be independent. So you have to fix the whole set together. So that means you have to fix every set and design for that. So if there are 200 combinations, you design for 200 times and pick the maximum reinforcement. So we never design for envelope. We design for all steps and pick the maximum reinforcement and use that. For column, type like active load, electrical load, here and then y. For heavy load, here and so. So we have all kinds of combinations in sets. So this part of going from loads to the design action sets is a long one. Now imagine you're running non-linear time history analysis, which we will talk about later. You will get thousands of actions because at each stage of the ground motion, we are calculating each acceleration step, we are calculating all the forces. And one earthquake has 4,000 steps, let's say, or 2,000 steps. So the structure is being analyzed 2,000 times for every acceleration step. Every time all the interaction, all the combinations are being considered, you're getting hundreds of thousands of load combinations for each column and then getting reinforcement out of that. So it becomes a huge task in the end. So let's get back to now how all of this is done over a period of time, because this looks quite complicated. It wasn't that complicated, obviously. I was looking at a video somewhere of the design and construction of the Empire State Building, 1920. All this knowledge wasn't there, what I'm talking to you about. No computers, no ETACs, no software, no SAP, nothing. They designed that tallest building, almost 90 floors at that time, using just hand calculation and simplified procedure. And one of the reasons that worked at that time is steel. If it was reinforced concrete, they would not have been able to do, because steel, you can still use elastic design for most of the things. And they didn't have earthquake. So of course, it's highly over-designed, based on the current design standards. But the point is that it was only done on limit on allowable stress to achieve factor of safety, this level. So they just check the stresses, and based on those stresses, they make all their design. So stress check was the final check, that whether the steel stress is within limit, combined stress is within limit or not. Then came the partial factor of safety method was changed, was introduced, because this was not enough, because people found, we have discussed this in the previous class, and then formulation of ultimate strength design came in when reinforced concrete started to be popular. Then the definition between brittle and ductile came in, and then changed. Then capacity-based design came because of that, and then from there performance-based design, and then now after that risk-based design, many other methods. So gradually over the period in last 100 years, we have gone through many cycles of different ways to do things, every time becoming more complicated than the previous one. So these are the design approaches that we have gone through. Intuitive design without any calculation, people did that before anything. So people just thought, this looks right to me. Based on their judgment, they will do this. Then code-based design, codes came in 1950s, 30s, 40s, they start to be developed based on the sketch checks. I remember CP114, British Design Code from UK, was very popular. It was this size, pocket size, looks like people can carry, and it was like 20 pages, the whole design code. That was enough, because it's so simple, there's nothing to do, there's just few things. Now the design code comes in volumes, you can't even carry them, right? They're so complicated. Every time the new version comes, it's more complicated than the previous one. because we have more knowledge and we have more things to do. So code-based design becoming more and more complicated. That's why, and it's still not reliable for tall buildings. So people move to performance-based design for tall buildings. Now most of the people are moving to PBD, performance-based design. Wind is locked into code-based design and because it's elastic. And then we have consequence and risk-based design and then resilience-based design moving forward. As I mentioned to you, we are moving forward and many people have already gone here, some have gone over there. There are resiliency council and things like that. So people are doing, depending upon where you are, how much you know, how much you can do, how much you are paid, people are going to that level. But the minimal is code-based design. So in this class, we will remain at that level. We will not be able to, we don't have the time to do the performance-based design work. So and the wind is also catching up. Some people are doing wind also, performance-based design for wind also. We have done a couple of pieces here and new codes are coming up which allow you to do that. So performance-based design is basically to check the intent of the code. The code intent, I told you, is safety. But once you design, there's no way to verify that the building is safe or not. You can only say, I follow the code. You cannot say anything more than that. You cannot guarantee that the building is safe. Except you can say that I follow the code. So if somebody comes, write me a certificate, the building is safe, you cannot write a certificate because you don't know. All you know is that you followed the code. But if you want to find out whether it's really safe or not, then you need to do performance-based to ensure safety. We need to do all of that. We need to go into detail, prescribe the limits, do the nonlinear analysis, find out the real earthquake, not use the maps, not use the wind velocity, measure everything, get the real loading, get the real material, don't use design material, so on and so forth. So we do the very detailed analysis and very detailed evaluation until we can satisfy ourselves, oh, this will be fine. Okay. So that is the performance-based design, that you check the performance criteria one by one yourself and don't believe the code. So that's the idea. So why people are moving to code? First of all, the code rules are too restrictive because they want to be safe, because they don't know what you're building. And most of the time, the buildings cannot be designed if you follow those rules. For example, the biggest rule is that if you want to design a tall building, you cannot use flat slab in earthquake zones. But flat slab is the most common flat system because it's cheap, it's easy, it's all of that. So if you want to use that, you have to prove that it will work. So you have to go to performance-based design to prove that even though I'm not following the code, I can verify that this will work. And there are many other ways, many other things like that. So that's why we need to make sure that the safety is defined for that building and verified properly for that building, the correct characteristics and locations and materials and systems and everything. So in the code base, you have objectives, you have requirements, and you have solutions all given to you. The document tells you what you must do, what follow, which load you should apply, which analysis you should do, what design you should do, what procedure you should follow. And tick, tick, check, and you're done. But but still at the end, you don't know if it will work or not. Because all you did was check, and you have to assume that the code is okay, but code is not okay for most of the buildings, tall buildings especially. So for that one, you have objective requirements and then alternate solution. You can just check several solutions and then verify the objectives one by one. Okay? So we don't have time to go into this. Maybe in the end of the class we might have, but in the meantime, I just want to mention that earthquake and wind from the performance point of view are very similar. Please watch this a bit carefully because this will tell you how the code and actual situation can vary. So let's start with the earthquake. So for earthquake, we need to do a site-specific hazard study. That means you cannot take the map from the code and take the zone from there for your building, because those zones are designed, generally, they are rough estimates. So if you want to really design a tall building for earthquake, you need to do the investigation for that particular location with that particular soil and all the layers underneath that all the way to the rock to find out how the earthquake will reach here and how it will respond. So that's called site-specific seismic hazard study. Then we design the building not for just one level like the code. Code gives you a certain force and you design for that. You check the building for at least 2 or 3 levels. One is a service level earthquake and one is a maximum terrible earthquake. So service level earthquake is which can come regularly, not regularly, can come often, for which the building must not be damaged. There are certain different criteria. So rules for service level earthquake are different for the rules for the maximum terrible earthquake which can damage the building but is not allowed. So two different earthquakes, significant and difficult design this earthquake is not real. This is real, that is real. Service level is the one which comes often. The MC is the one which will make come one, maybe only 2% chance that it might come in the life of the with a very low probability, high intensity. Then we get hazard etc. And then the long motion, time history, so we simulate everything, actual earthquake, hitting the building, and then we analyze the building for that. On the wind side, we do a site-specific climate analysis. Once again, we don't believe the wind. You get the wind profile from the weather station in that area. Based on that, you do a climate study from there. And from there, various events, areas, and properties, and everything. When you wind, this was different to wind, and then you run it for wind magnitude. So the two are very high in terms of the effort, but also the liability is. So if you get enough, paid enough, you should see it. And these are the guidelines that you can use. Different from these normal codes. You can see SCI code, the code a lot in this. Normal building codes do not work for tall buildings. There are separate guidelines for tall buildings that you can use. What common is the CDR? Guidelines for performance-based design for tall buildings, then alternate user seismic regulation, and all of that. So many guidelines are there. So people have to use and study these guidelines. Use this. If you want to get more information, you can watch these videos on why the seismic design is unique and how it is used and what it is. So this is each 30 minutes long, so you can get an idea. Okay, coming back to our course and our project. So for our project or our course, we will be doing something like this. You will start with a building, this is the architecture plan, or you will take a sample building, modify it, or you will get some plan. Try to be real as possible. Take a real project as your sample. Don't create an artificial, because it will be very hard for you to do that. So take a project and then from there develop the structural system of that project, then create the finite element model. After you find the sizes, as I mentioned, you estimate the sizes. Based on that, you create the model in ETABS, and then from there you will run it, do the analysis, get the forces, get all the design actions and bending moments and displacements and maintenance period, all of that stuff. Then from there you calculate the reinforcement, that's a reinforcement calculated. From there you can do the detailing using ETABS detailer, and then get the drawings, sections, design some column, design some beams, get the details, and then from there you can get the whole cake and you can put it back onto the Revit if you like. But the question will still remain, this is fine, this is one cycle, you finish according to the code. But the question will remain that what is the performance of this building? We don't know. And that can be checked by either performance-based design or through structural health monitoring by putting sensors on the building and measuring its response. So many times buildings of importance, structures of importance, they have sensors attached to them. So you can measure their response through their life and check their performance. So that's how it will work. So structural health monitoring, very important subject, very, very common, very popular now. So you basically attach a lot of sensors to the buildings and then monitor the health of the structure either regularly or every year or every 6 months or every 2 years. Go and do the annual checkup, right? Or you put the sensor like this one tracker, when you walk around, you get the data all the time. So either you have a tracker in the building or you have annual checkups, go to the hospital and everything. So that's how the building's health monitoring is done. It's very close to human health monitoring, very similar, right? So that's quite important for important structures. This is, for example, just to give you an idea how the structural health monitoring can work at a city level, like they implement in California and some places. We try to do it in Philippines. So you have the sensors in the building, you measure the actual after the earthquake, you get the results, you check the response, you have all the model, and finally you can do real-time reporting whether something happened or not. So based on the response of the building, you can detect, you can determine whether there's a damage or not. No need to inspect. You will know from the analysis that certain thing will be damaged or not because you have already got the model, you have a real ground motion, you have the whole thing, and you can predict this will cause any damage or not by sitting in the office. So that's the kind of thing that you could do if you have done all of that stuff that I mentioned to you. Okay. So that's the overview of the design process. So design criteria is very important because this will set the rules for your design. Everything, which node you will use, which method you will use, which software you will use, what soil you will use, what criteria will you use, everything that you're going to do, you will write down first. That this is my project, these are my rules, this is what I'm going to do. And then follow those. So that anyone who is checking your design can check your design based on your design criteria. So normally for a big project, the consultant will develop the design criteria and send for approval to the client, to the authorities, to other engineers. So they say, okay, what you're going to do seems right, go ahead. If anybody has an objection, they can say, no, the model should be like this, road is not correct, this is not correct. So they make the correction in the design criteria. Once the design criteria is locked, then you just follow it. So then save time. And also people can check. Okay. So most of the time the debate is about design criteria. Debate is not about the actual design because then people will just follow that. Okay, key structural systems for tall buildings. We already discussed them. I'm just going to review them one more time in a systematic manner with a little bit more detail. And I'm going to introduce what is called the 4 commandments of tall building design. What's a commandment? Yeah, ordering, this is based on the 10 commandments, sent by God to Moses to follow, from the street. But these are the rules that the designers are encouraged to follow. If they follow these 4 rules, they will likely get a good design, a good system. So that's why we call it commandments, that you must follow these 4 rules to get a good system working. Okay. So the first one is that vertical elements should be spaced as far from each other as possible, from the center of the building. So you should have the base as wide as possible, of course. This is, of course, you want it, but you can't get it because architects will govern sometimes the slimness building. So whatever is your constraint, your structure should be as far out as possible. That's why diagrade works very well. That's why the surface elements that I showed you last time work very well, because they put the structure at the skin of the structure, which is the farthest possible from the center, at the boundary of the structure. So which means tubular system, diagrade systems, these systems put and bagger column systems, they put the structure at the outermost edge of the structure of the building to take the maximum benefit from that. So that's number 1. Commandment number 2 is that the gravity load should go to the same elements which are resisting the lateral loads. Because why should we put the gravity load on the same element which is carrying the lateral load? You might think, why are we putting double load on this is poor column or poor element? What is the reason behind that? to resist the overturning, but also to reduce the tension. Because especially for reinforced concrete buildings, we don't want tension in the columns. So it must have a lot of gravity load that when the building will be overturning, it should not go into tension. So the gravity load should balance the tension by adding the compression from the gravity load. So we channel the gravity loads also to the same elements which are responsible for lateral loads to prevent overturning, number one, and then secondly, prevent tension in the column, which is never good. Then link the vertical elements together with shear resisting structural element. This is very, very important. Well, probably one of the most important element of the tall building design is that vertical elements should be connected together through shear elements. So they can share the lateral load and distribute it amongst them. This is called the outrigger and the link beam effect. Okay. And this is the cornerstone of a design. Without that, tall buildings just won't work. Okay. You have got to do this kind of and this is also to prevent shear lag. We studied about shear lag last time. We'll come back to this again. So this is to prevent shear lag and also to make sure that you make the farthest elements connected to each other through shear. They can, the strain, so to speak, the deformation between them can be compatible. So there's no leakage of displacement. So building deforms as one, not like, I showed you last time the book example, right? Those slices of paper. So each column should not be a slice of paper. They should all be glued together, and that is the glue. These horizontal big shear elements are the glue that will bind all the columns together from one face to the other. And last one is that resist the lateral forces, axially loaded compression by gravity load. This is related to number 2, that we should make sure that axial forces resist the bending moment, not the bending moment capacity. You cannot design a tall building for bending moment by resisting the bending moment by bending moment. You need to convert the bending moment into axial forces. That's the only way to resist the bending moment. Like for example, if it's a cantilever, simple cantilever, like this one here, if I apply a load here, bending moment, the section capacity will resist it. So bending moment of the cross section will resist the bending moment from the external load. But for tall bending, it cannot be like that. Tall bending, if I have a bending moment, it should be converted to axial for tension and compression at the column. So the bending moment should be resisted by tension. Of course, in this section also the same thing. Bending moment will be converted to tension and the compression, but still it's the bending moment to section. So in our case, we must convert that into the ultimately tension compression as the outer surface. So the other 3 commandments, actually, all of them follow similar rule, similar idea. That lateral load, when it comes, we convert that into axial forces, space as far out as possible, interconnected, make sure that they do not slip, there's no shear slippage, no shear lag. So that's the key concept of the tall building system. If you follow these, you will get a good thing. Okay. So having done that, the next one is the important. Beat the math. Math is saying 1 plus 1 is equal to 2. But engineering will say no, 1 plus 1 is greater than 2. And that's how you bring efficiency to the system. You beat the math through engineering. Which means that when you add 2 systems together, the sum of those 2 systems should be more than the individual simple arithmetic sum. So if this is one column and one column with the stiffness A, stiffness plus 2 and 2, the total stiffness of the structure should not be 4. It should be 8 or 10 or 12. And that's the key, that you add another element which is coming back to the previous commandments, but now into a little bit more detail. So we have to always think of that. How can I increase the sum of the stiffness to be more than individual sum? The total stiffness to be more than the sum. And ductility and everything in the same way. So it works in the same way. So we have to be innovative in adding things together. How does that work? For example, if I have two walls here and I just connect them by links, then the stiffness will be 1 plus 1 equal to 2. Stiffness of this column and this wall add together, total stiffness will be equal to 2, because each of them is bending independently at the same time. But if I add these two elements between them, this will prevent them from bending independently. It will become one structure. There will not be two walls. There will be now one wall with connected system. So now the stiffness is equal to 8 actually, suddenly. What does it mean? That if I apply force here and the displacement, same force, this displacement is, let's say it is 8, displacement will become only 1. I did nothing. I just connected them by those two elements in between, and the displacement reduced by 8 times. Right? So the sum of the two stiffness now is not 2 but 8. Total stiffness of the structure is 8 rather than 2. So that's the kind of thing that we are always looking for to do in a structure. How can we increase the structural stiffness or structural performance more than the sum of the individuals? Okay? And that's the key. And that's why some structural engineers are better than others, because they can do these things better. They can find the solutions to this kind of thing, okay? Innovative stuff. And people have been doing that. Over the years, all structural system development is related to this one. Somebody found some way to cheat the math, right, by engineering. So one thing to do that is called the coupling effect. So we couple things together. One way to get more than 2 is to create a couple rather than individual independently, right? So you connect them together. This is called coupling beam or coupling effect. So two walls independently, instead of that, you couple them, connect them together. And these coupling beams become the most critical part of a tall building design. Similarly, if there's a frame and there's a wall, connect them together by coupling beams. Okay? And these coupling beams will suddenly increase the performance of the structure in almost every way. Reduce the drift, reduce the natural period, increase the ductility, increase the stiffness, just wonderful. And so these link coupling beams become they are the friends of the structural engineer. So if you want to design a tall building, look for your friends, which is coupling beams. Where you can place them strategically, how you can design them, but also they're very hard to design. Very hard to design. And the reason is earthquake and wind have different expectation from wind beams. Wind will expect them not to yield. And if you put them, wind will give a lot of force. And you have to design the coupling beam quite big. As soon as you increase the coupling beam size, it attracts more force because it's stiffness based. And then you increase the size. Ultimately, it becomes too big and you cannot even have the room to go through. So you end up with a problem of controlling the size of the coupling beam. Because when you put the beam, elastic stiffness demands that the force will be equal to stiffness. But earthquake, we can allow them to yield to be nonlinear, like I showed you that curve. So we don't care about that. We just make sure that they are there and they have the capacity. So, but the problem is if we allow them to yield, wind will not allow us to yield. And then the structural engineers are always caught in this dilemma, how to design coupling beams that satisfy the wind and earthquake. It's a big challenge. So ultimately, we almost always come into this difficulty of designing the coupling beams. And there are codes that have done many things. You put that kind of reinforcement, you do that, you do that, you do that. Many things are there. Steel, you replace them by steel, you replace them by dampers. So there's so many ways to handle this problem. But this is the biggest opportunity and challenge at the same time. Second one is the outrigger effect. These are the two things that you can repeat the math. One with using coupling, and second by activating the outrigger effect. So outrigger effect is the same that if I have an arm here, if I'm bending, if I put a stick here, or have somebody I will increase my stiffness by transferring my bending moment in my body to the axial force in that stick through the stiffness of my arm. So that's exactly the outrigger effect. So we always have these arms coming out of the core wall to the outer column, try to engage them to stabilize myself. And once we do that, we have the outrigger effect, right? But once again, the problem is the same. These outriggers will block the whole floor. How can people go through? It's a big beam, 2 floor. Normally they're 2 floor high. So they will block that. You cannot do anything. So outriggers have a problem of creating architectural challenges in the building. Architects just don't want them. Nobody wants them except you. So we have to work around that. There are many ways to. So we will talk about the outriggers as a separate topic. Both coupling beam and outriggers, we will go into more detail. But outriggers and coupling beams, these are the two mechanisms you have to create innovations in the system and solve the problem that you will definitely have in your building. But how you use them and how, so there are ways to handle these kind of things, but we will talk about that when I talk about outriggers and belts and things like that. So outriggers are the most effective tools for satisfying key design principles or the KPI. So what are the KPI? These are the 10 KPIs. Once you finish your project, you should check all of them, right? Start from stiffness, should have enough stiffness, but not too much. Stiffness is good for wind, not so good for earthquake. So right stiffness. Stability should not fall down, should not overturn, should not strength, should not break in shear or something, must be strong enough. Deformation should have the ability to deform, but not too much. The drift, it has a drift, horizontal, it's drift, but not too much, certain drift. So one of the key control is drift. If you control drift, you control many things in tall building. So if you're a tall building designer, the first thing you're looking for is drift control. Because if you control drift, you will automatically control most of the other things. Because drift is a deformation control, and if you limit that, everything else will fall in place. So if that's the main target to look for, optimize or look for drift. Then ductility, independent from drift, damage, depend on that. Damping will help to control that. Energy dissipation, acceleration. So these are the 10 things you should be looking for in your building as a checklist. When you develop a system which gives you the best values for these is the system that you're looking for. So stiffness comes from material, section, member, configuration. Stability comes from stiffness, geometry, restraints, foundation, soil. Sex strength comes from material and section. Deformation controlled by stiffness, geometry, and irregularity. Drift controlled by stiffness, geometry, and irregularity. Acceleration controlled by mass, damping, and stiffness. Energy from damping from damage and material. Damage from ductility, from section and material. Ductility from material, section, and confinement. This is a total picture of everything in one slide. So you put all the things that you can do and all the criteria in one slide. So if you want to see what are the key KPI and how I can satisfy them, then this is a great guideline for that. Okay. Human perception of acceleration is very important. The last item I told you. So acceleration, normally we have to limit the acceleration to a small value. So 0.5 G, 5.5% of G, no perception, people cannot feel it. And if it is more than 15%, then people will just not be able to tolerate it, fall down, right? So we have to keep, normally the limit is here, threshold, normally here, less than 1.5% of G. And if it becomes more, it's annoying, it's busy, people, and there's, especially in New York, there's a very good example. They've made this very nice building right next to the park, and then Central Park. Very, very expensive property. but very slender because the land was very small, but they built very tall. So obviously in wind, even if they put all the design and dampers and everything, it still has an acceleration which is slightly higher, and it creates a noise at night because when it drifts, the windows creak and the walls creak. So people who have paid millions of dollars are always complaining to the owner that when I'm sleeping, the building is making noises, right? So it's just the whole building, billion-dollar project, because of the acceleration and drift control, is now in trouble. So they have tempers, whatever. The point being that these things are very important. It's safe, it's not going to go anywhere, but it's annoying. Okay. So that's the thing that you should be thinking about.